So these were the three questions what we had in the midterm, and Sugata asked me that if we can discuss this. So let's look at these questions and see what is the expected answer for these papers. You might have your own answer, that's not a problem. But I'll discuss what we were expecting. I mean, the teachers, three teachers are there, so what we are expecting, we'll discuss that. Right? Okay, so let's go one by one. So first question, right. Consider a state function, which is this, sine theta and cos theta. Now, if it is a solution of an eigenvalue equation, so that is the operator A with the eigenvalue lambda. Predict the corresponding operator and eigenvalue. Okay, so let's say if I were you, what the way I would have thought, it's like that. Now, without getting into the much details, like if I look at this function, what does that give me some idea? Now this is kind of a function which I'll be getting like a particle in a box, right? So in case of a particle in a box, now people are still joining, and yeah. So in case of particle in a box, I know that my potential was V was 0. Right. So that is my assumption. I'm like not forcing you to do this, but if you know the other option, you can do it. So that means the operator is having only the kinetic energy term, right? And kinetic energy term, of course, like goes like half mv square or p square by 2m. So p is again the first order differential d by dx. If I go like that, so here actually the variable is theta, so I should go along d by d theta. Now p square when I do, so that is going to be d2 by d theta square. Right. So that is I mean, like it's coming just like my thinking that this is going to be kind of particle in a box function, and so therefore I have only the kinetic energy operator, of course with the constant term, so I am not going to worry about that here. Now if we take this function now on this, right, so that is going to be so this is like if I do the derivative twice for this, now this, what is this, numbers are going to be remaining the same, so I'm going to get first derivative if I do, so I can split it like this, d by d theta, and then this is going to be square root of 2. Now sine theta, if I do derivative first time, that is going to be cos theta, right? And then plus I'll have the constant again 1 by square root of 2, and then cos theta is going to be minus sine theta, right? So you have to remember that. Right, so that was the first derivative. So this part you are getting minus. Now if you do again derivative one more, then what you get? Now this part you get the minus sine theta, this remains same. So here you will do one more time, you get minus sine theta, right? And then here you get cos theta, sine theta become cos theta, and this minus became minus. So overall you are going to get the function which is -1, and when you get back this, so that is nothing but this function, so that is this, right? So from this obvious is that like operator A is going to be d2 by d theta square, and eigenvalue is going to be -1, right? So that is the answer we are expecting from the first question. So okay, now next question is that consider two degenerate states phi 1, phi 2 of energy 0.5 Hz, half a Hz, right? So half a Hz means you can think about hydrogen atom. So this is one, this is another hydrogen atom. So half a Hz for a given system. What would be the corresponding energy of an arbitrary state, this, which is nothing but the linear combination of 1 into phi 1 minus half or 0.5 into phi 2, the system? Justify your answer, right? This question, I don't know, a lot of people have done the mistake. I don't know what was the reason, but the answer is very simple. Like if you look at, if I am having degenerate states, so what does that mean? So that means I am having the same eigenvalue for these two, right? So that means I'm going to have something like operator A, if I take, right, phi 1, so there is operator sign here. So I'm going to have 0.5 or half, and then phi A1. Similarly, I'm going to have exactly same equation for phi 2 also, right? So I'm going to have A phi 2, and then 0.5, and then this, right? So they're degenerate. Now if I take the linear combination like this, right, so you can very easily work it out. Like if I operate now A over psi, right? So what exactly you are doing now, if I put psi this back here, so I'm actually doing operator A operating on phi 1, then I'm going to have minus again operator A operating on this 0.5 and phi 2. Right. Now look at here this equation. So when I operate on this, what do I get? I get 0.5 and phi 1, right? So if I write it here, so first term is going to give 0.5 phi 1, right? And then second part, this 0.5 is constant. Again, I'm not going to do it anything. Now if I operate on phi 2, I get again 0.5, right? So I'm going to write minus 0.5 and this 0.5 remains unchanged. Phi 2 is going to come back, so I'm going to put it back again 0.5 and phi 2. So I don't have space here really, so that is the case. Now if you take this 0.5 here common, so I'm writing it here. So I'm going to get phi 1 minus 0.5, 2. That is 2, right? So if I get this, then what is this? This is nothing but your 0.5 and this function back. So this is not 5, this is actually 5. Sorry. So that is basically psi I'm going to get back. So therefore you can see is that this is going to be the eigenfunction again with this same function back. So I said that what would be the corresponding eigenenergy of an arbitrary state this, that is going to be same, right? So it's going to be 0.5. Okay, now this basically, I think you could recall this. I don't know if it was discussed by Professor Boliram or not. Like when you generate the px orbital is a real orbital. We convert this from the p solution, that is p plus 1 and p minus 1. Right. Now we say this is going to be x if we take the linear combination, positive linear combination, that is going to be, it's not exactly equal sign, this is going to be approximately. So this is the linear combination of this. Now this and this are degenerate. Now when you take the linear combination, that gives the positive combination and we are going to get the px, right? So it's exactly the same thing. So if you have two degenerate function, if you take the linear combination, the function is going to be again the eigenfunction of the same operator with the same eigenvalue, right? So that's what again. Similarly, if you go for py also, this is going to be the minus combination, right? So that's what is the that was the idea. I think I mean you could have think about this. Now I go for the last one. Now this one also some of you have done mistake. I don't know. Again, the only trick was like the probability density. Right. So we said to consider an atomic orbital of the form. Now looking at this form, we could have understand this is going to be kind of s orbital, right? So normalization constant e to the power minus zeta r. Now zeta, if you are taking 1, that is going to be kind of s orbital. So I said sketch its shape. So that means it's going to be a spherical orbital. So shape, if you want to sketch it, going to be spherical. Sorry, my drawing is not good. So that is spherical orbital, right? Okay. Yeah. So yeah. So yeah. So I said that sketch its shape. Shape is going to be definitely spherical because it's going to be s orbital. Next part was locate the position of maximum probability density for an electron in this orbital. So probability density, not the probability. Look at this part, right? So, so if you plot this is exponential decaying function. If I plot this, right, with respect to r and this psi, so decaying function is when r is 0, this is going to be 1. So that value is going to be 1 by square root of pi. Let's say that is somewhere here, right? And then it is exponential decaying function. So it's going to be going like this, right? Now I asked for probability density. Now probability density is basically is going to be the just square of this function or mod square, right? So probability density, if I go for this mod square, so that will be maximum at r equals to 0 itself, right? But most of you, what you have done the derivative and set it to 0. So what you have tried to plot this one, right? But this one is the probability, right? So that means you have this one. Okay, let me change the color. So this curve, what you are referring to is basically multiplying with the volume element 4 pi r dr, right? So that is 4 pi r and then multiplying with the dr, right? So that is the volume element. So when you do that, then you get this one, and that is the way we say that hydrogen cannot have electron at the nucleus. But actual probability density is when you get psi square, that is nothing but this one. Right? So that was the mistake. Some of you have done this. So that is now why in case of an atom we get an infinite set of atomic orbitals. That answer is very simple. Like when we go for h psi equals to e psi for atom. So that for atom this is h, and then let's say I'm going for phi, then we get epsilon phi, right? So in this case, this is a Hermitian operator, right? And in principle, when it is a Hermitian operator, this function is going to be a complete set of functions. Now, complete set of functions are nothing but infinite number of functions which are orthonormal, right? So therefore, in general, you are going to get an infinite solution when you do this. Of course, you might ask, it should be holding for the same for the molecule, right? Answer is yes. Right. But when you here it is when you did the molecular orbital, I think one missing term we could have given you LCAOMO, right? That's what I think Dr. Opsit had discussed, right? LCAOMO, right? So in case of LCAMO, you only consider the 1s A for one hydrogen atom, and then you have taken the linear combination of 1s B. So that was your guess function for LCAOM, right? So therefore, as you are starting only with the two atomic orbitals, so you'll be ending up with the two molecular orbitals. That's quite natural. So that is basically the way you are starting with your guess function. Now, if you would have taken the guess function, which is going to be linear combination all of the infinite numbers of atomic orbitals, which you get it from here, you could have got the infinite number of molecular orbitals. Okay, so that is not a problem. Again, go for the second part. Second part, it says the explain the effect of relative atomic orbitals to account for the solution of a molecular orbitals, right? So this is very simple. I think it could have just by drawing this. Like if I have homonuclear diatom consideration like that, so you are have both the orbitals at same level, and the energy stabilization when you form the MO, right? So that stabilization energy is going to be more compare if I consider two heteronuclear atom, something like that. Let's say this is the case. Then normally what happens, your stabilization is going to be like this. Now here actually stabilization energy you get with respect to this, so that is the lower. So if you take the average of these two and then if you measure, so that's why this value is going to be less. So average is somewhere, it is going to be, let's say, somewhere here. And if you are taking this, so this height is less than the height what we are going to get it from here, right? So that is the simple way I think I would think about that. If we go for the relative energies of they are at the same level, so the stabilization is going to be more compared to the one if they are going to be at the different level. I think that's what Dr. Rokshid would have been expecting. The this one is a electronic energy with and without internuclear repulsion for ground electronic state of H2 class, right? So if you electronic energy, if you think about, so if I plot this, this is the electronic energy. I'm just writing E. This is the separation R, right? R A B. If you think about, R is coming in this direction. Now, if you are thinking about without internuclear repulsion, only electronic energy, so that is going to be the Coulomb attraction plus the kinetic energy component, which is going to be something like attractive potential, and it will come to the value 0.5, right? Minus 0.5, because I'm having only one electron, and if you solve it, it's going to be somewhere here, right? So that is minus half. But when you add repulsion to this, now as such repulsion term, if you look at here, only repulsion term is going like very slow repulsion when they are long distance, and then it is going to increase like that, right? It's going to go when it goes like this. So it cannot come very close because you have nuclei. Now resultant of this and this after addition with the nuclear repulsion, then finally what you should be getting, the resultant curve, because addition of these two, and then you are going to get like this, right? So that is the, so this is without internuclear repulsion of electronic energy, and this is with addition of the internuclear repulsion. So this is repulsion, this is attraction. If you add these two, you are going to get resultant is this, right? I think that is the simplest way I would have thought. Right. Let me start and see how far we can go. Oh, yeah, I've come back. This one, right? Yeah. So here actually this construction of character table, I really don't need to do anything. This was done in the class. Only this we have to discuss, right? Now I think I have less than a minute, so this will disconnect. Only thing is that this is having like 2pz, right? Sorry. I think maybe we, once it disconnects, we'll reconnect it and we'll discuss this, right? It's going to disconnect this right now.